Every undersea tunnel ever built makes the same silent promise to the people riding through it. Trust the concrete, and don't think too hard about what's pressing down on it from above. That promise has held for more than a century, through some of the most demanding engineering projects on Earth. This is a story about someone imagining what happens the moment that promise gets broken on purpose. There's a reason that promise has always worked too. Most people crossing beneath open water actively don't want to think about how much of it is sitting above their heads. Fear of enclosed, lightless spaces is common enough that transportation engineers design around it as a matter of course, softening tunnel lighting, adding artificial windows, playing ambient sound, all in service of helping passengers forget where they actually are. This concept runs directly against every one of those instincts on purpose, betting that the exact fact people usually want hidden in the ocean, right there, inches away, could instead become the single most memorable part of the entire journey, if the engineering behind it were trustworthy enough to make people believe it. Start with a country that already proved the concept works. In 1988, Japan completed the Seikan Tunnel, 53.85 kilometers of railway running beneath the Chuguru Strait to connect the main island of Honshu with the northern island of Hokkaido, dropping to 240 meters below sea level at its lowest stretch. Nobody had ever bored that far beneath that much open, violent ocean before. Japan did it anyway, and the tunnel has simply kept working ever since, through decades of storms and tremors, because Japanese engineers spent the years afterward turning every discipline underneath that achievement into a genuine specialty. Earthquake-aware design, coastal mega construction, deep marine survey work, pressure engineering measured in fractions of a millimeter. If any country on the planet has the credibility to attempt something stranger than Seikan, it's the one that already built it. Seikan itself was not a quick or a clean win either. From the first geological surveys to the day trains finally ran through it, the project spanned roughly 24 years, fighting through unstable rock and flooding incidents that had to be sealed and pumped out by hand in places, and a toll of 34 workers who died during construction, a cost Japan doesn't advertise, but doesn't hide either. And one worth remembering every time a video like this one reaches for the phrase, engineering marvel, without pausing on what that phrase actually costs. And Seikan itself wasn't built for spectacle. It exists because of a tragedy. In 1954, a typhoon sank the ferry, Toyomaru, and 4 other vessels crossing that same strait, killing more than 1,000 people in a single night. Japan's government responded by deciding, within years, that ferries crossing that strait would never again be the only option, whatever it costs to build something safer. That's the emotional core sitting underneath every fact in this video. Japan doesn't attempt undersea megaprojects for the headline. It attempts them because, once before, staying on the surface got people killed. Japan's relationship with undersea crossings didn't start there, either. Decades earlier, engineers had already bored the Kanmon Tunnel beneath the strait, separating Honshu from the southern island of Kyushu, first for rail and later for road traffic, proving as early as the middle of the 20th century that the country was willing to put infrastructure directly under moving water rather than over it. There's a second, more recent precedent worth knowing too, because it previews the exact hybrid this concept borrows from. In 1997, Japan opened the Tokyo Bay Aqua Line, a crossing that runs as a tunnel for roughly the first 10 kilometers under the bay and then rises onto a bridge for the remaining distance, transitioning through a genuine artificial island called Umihotaru, built specifically to host the ventilation systems and service facilities. A project like that needs partway across open water. Bridge, tunnel, artificial island, stitched into one continuous crossing, Japan has already built exactly that shape once. This concept doesn't invent the structure. It just asks what happens if you make the tunnel section of that same structure transparent. So here's the stranger idea. What if the tunnel itself simply disappeared? What if the only thing standing between a passenger and the open Pacific was a curved, pressure-rated pane of glass a few centimeters thick, and the entire experience of crossing beneath the sea stopped being something you endured in the dark and became something you actually watched happen around you? None of this would be believable if humans had never experienced anything like it before, even at a tiny scale. Aquarium visitors have walked through acrylic viewing tunnels with sharks gliding overhead for decades. A handful of resorts, including an underwater restaurant built into a reef in the Maldives, have already proven that curved, transparent structures can survive real ocean pressure while people eat dinner a few meters beneath the surface. Dubai has built underwater hotel suites, facing directly into open water. Japan itself already has a domestic version of this instinct on a much smaller scale. Several of the country's public aquariums, including large facilities built specifically to showcase whale sharks and manta rays, already route visitors through curved acrylic tunnels, engineered on the same basic pressure principles. This much larger concept would simply need to scale up by several orders of magnitude. All of those examples are small, shallow, and contained. Nothing close to a multi-kilometer transport corridor holding back an entire strait. But they prove the core sensation is real and survivable. People already pay money to stand inside a transparent structure with the ocean pressing in around them, and they already trust the engineering enough to do it. This concept just asks what that feeling looks like stretched across 50 kilometers instead of 50 meters. Before we go any further, I need to be straight with you, because this next stretch is not a report on something already under construction. This is a concept, a deliberately speculative vision of undersea travel, built with as much real engineering logic as I could load into it, but not an announced, funded, or approved Japanese infrastructure project. Consider it less a news story and more a working blueprint assembled from materials and methods that already exist today, just never combined quite this way before. Let's build it piece by piece and see exactly how far real engineering can carry an idea before it stops sounding like fiction. And since we're being honest, here's the number that probably explains, better than any unsolved engineering question, why nothing like this exists yet. Even a modest few kilometers of pressure-rated transparent tunnel would likely cost several times more per kilometer than a conventional bored tunnel, purely because of the materials, the redundant testing, and the sheer novelty of manufacturing glass and titanium modules at this scale for the first time anywhere. A full crossing could plausibly run into the tens of billions of dollars before a single passenger ever boarded. Picture the route running between a mainland coastal city and a colder, more remote island shore to the north. Real currents, real winter storms, the kind of unforgiving water where Japanese marine engineers have already spent half a century proving exactly what they're capable of. Before a single tool ever touches the seabed, before any tube gets lowered into the water, engineers have to answer the questions that decide whether the entire idea is even physically possible. Where is the seabed actually stable enough to build on? How strong do the currents run at depth? What layers of rock, clay, and sediment sit beneath the surface? And can any combination of them support a structure required to resist crushing pressure every second of its working life? For decades, without ever taking a day off? Survey vessels go first. Sonar arrays, floating buoys, seabed sensors, geotechnical drilling rigs, and remotely operated vehicles spread out across the strait, quietly mapping terrain. Nobody topside can actually see, recording depth, slope, current, and soil behavior, meter by careful meter. The tunnel doesn't exist in any physical sense yet, but its future route is already being sketched across the seafloor in raw data, markers, and engineering judgment, long before a single truckload of concrete arrives. This phase alone could easily run years before anyone breaks ground, because a single wrong assumption about seabed composition, discovered only after fabrication has already started, could force a total redesign of the anchor system. Engineers would need core samples pulled from dozens of points along the route, current data gathered across every season rather than just a calm summer window, and computer models capable of simulating how a strait like this behaves during the worst storm it's likely to see in 100 years, not just an average one. Institutions capable of running that kind of research already exist in Japan today, too. Bodies like the Port and Airport Research Institute already study exactly this category of problem: marine structural engineering, seismic resilience in coastal construction, wave force modeling for entirely conventional harbors and breakwaters. A concept like this wouldn't need invented expertise so much as it would need that same existing expertise redirected at a stranger question than usual. Then the unglamorous part begins, and it stays deliberately unglamorous, because this stretch has to be boring in the best possible sense of the word. Temporary roads, staging yards, cranes, power stations, drainage systems, and control facilities rise along the coastline. Reinforced concrete approach tunnels get bored downward from the surface, angling toward the sea, built from the same techniques Japanese crews have executed successfully for generations. Concrete lining, steel reinforcement, waterproof membranes, rock bolts, ventilation shafts, drainage channels, emergency systems. Every meter of that early tunnel gets driven forward using the same incremental method Japanese crews have refined since Seikon and Kanmon. Excavate a short section, immediately reinforce it, seal it against groundwater intrusion, then repeat, never advancing faster than the ground itself can be trusted to hold. None of it is meant to impress anyone. It's meant to work without fail, forever, because everything stranger that follows out at sea is going to depend on this backbone holding. The genuinely extraordinary part of the concept gets built somewhere else entirely, in coastal fabrication halls, far from the water, where long cylindrical transparent modules slowly take shape. These are nothing like glass boxes bolted together. Every module is engineered round, on purpose, because a circular cross-section spreads water pressure evenly around its whole circumference instead of concentrating stress in the corners the way a rectangular structure would. The physics behind that choice is worth sitting with for a second, because it isn't abstract. Water pressure increases by roughly 1 additional atmosphere for every 10 meters of depth, which means a structure sitting 40 or 50 meters down is being squeezed by roughly 5 atmospheres of pressure, pushing in from every direction at once, all day, every day, for the structure's entire working life. A flat pane, under that kind of load, concentrates stress at its edges and corners, exactly where failure tends to start. A curved pane spreads that same load evenly across its whole surface, which is the entire reason submarine viewports, deep-sea submersibles, and now this concept all converge on the same basic shape. The glass itself wouldn't be a single sheet, either. Realistically, it would be laminated, several layers of tempered glass bonded together with a flexible polymer inner layer, the same basic principle used in bulletproof glass and aircraft windows, so that even if the outermost layer developed a crack under years of cyclical stress, the layers underneath would keep holding the line while sensors flagged the panel for replacement long before anyone on board was ever in danger. Titanium gets chosen for the ribs and rings for a related reason. It resists seawater corrosion far better than steel over multi-decade timescales, and it carries an exceptional strength-to-weight ratio, which matters enormously when every extra ton has to be floated out to sea and lowered by crane instead of simply poured in place. Base isolation, a technique already standard in Japanese skyscrapers and bridges, uses flexible bearings between a structure and its foundation to absorb seismic energy before it ever reaches the structure itself. A version of that same idea, adapted for the joints between rigid concrete tunnel and flexible transparent modules, would likely be essential here too, since the two materials would respond to an earthquake completely differently, and that joint is exactly where the mismatch would try to tear itself apart if nothing absorbed the difference. Each one is built from repeating rings of high-strength titanium alloy, longitudinal titanium ribs running the tube's full length, curved multi-layer pressure-resistant glass panels fitted between them, waterproof polymer gaskets sealing every seam, circular end flanges for joining to the next segment, and a full protective shell wrapped around the outside. This is exactly why the fantasy holds together instead of collapsing into science fiction. Nothing here gets treated as magic. It's presented as the obvious next step for materials that already exist. Stronger alloys, sharper structural sensors, deeper and more rigorous pressure testing, modular assembly borrowed straight from shipbuilding and aerospace. Inside the fabrication hall, titanium rings get machined, inspected, coated, and assembled into full circular frames. Curved glass panels get lifted by suction rigs and set into the ring grooves one at a time, each one following identical cylindrical geometry, slowly closing the tube wall into a complete circle. Waterproof seals get compressed along every edge, with a secondary anti-leak gel applied around each glass to titanium seam as a backup layer. Circular end flanges get bolted on so every finished segment can eventually join its neighbor out at sea. Every weld joining a titanium ring gets inspected using ultrasonic and radiographic scanning before it's ever allowed near the water, because a hairline flaw invisible to the eye is exactly the kind of defect that only becomes a problem after years of cyclical pressure loading. Quality control on a project like this wouldn't sample a percentage of welds and call it good enough. It would check effectively all of them, because a transport tunnel carrying passengers under an entire strait doesn't get to fail safely the way a shipping container might. Every individual glass panel would need its own certification too, batch tested to destruction and a sacrificial sample from each production run. So the panel actually installed in the tunnel is backed by a twin that was deliberately pushed past failure in a lab, just so engineers know exactly where the real safety margin sits, instead of trusting a number on a spec sheet. No module gets anywhere near open water without surviving pressure testing, designed to be far harsher than anything it will actually face once installed. Each completed tube gets lowered into a curved test cradle, shaped to support its round body properly, while pumps, sensors, hoses, and inspection equipment simulate deep ocean pressure against every surface at once, and engineers hunt for leaks, deformation, seal weakness, flange movement, and glass stress down to fractions of a millimeter. Only after clearing every check does a module get moved onto a marine transport cradle and hauled toward the dock its last dry moment before the sea. Offshore, everything turns dramatic at once. Floating cranes, barges, survey boats, and underwater robots gather above the planned route. None of that offshore work could happen on just any day, either. Lowering a multi-hundred-ton glass and titanium module into position demands a genuine weather window, calm seas, minimal current, and a forecast stable enough to guarantee hours of uninterrupted work. Because halting a module halfway through its descent isn't really an option once the process has begun. In a strait known for real winter storms, that might mean crews spend as much time waiting for the right conditions as they spend actually working. With entire installation schedules built around narrow seasonal gaps rather than a simple calendar. Down on the seabed, anchor bases sit ready, already protected with anti-scour rock armor. The first module descends slowly off its barge, sinking through water that turns bluer and colder with every meter, guided the entire way by remotely operated vehicles using lights and robotic arms to keep it perfectly aligned. It hovers just above its foundation, locks into guide grooves built for this exact moment, and settles the rest of the way down until its support shoes lock into place. Hydraulic clamps close around it and anchor it in. Only once the whole structure reads fully stable do the crane cables finally release. Then it happens again. A second module descends. Its circular flange lines up precisely with the first module's. Waterproof gasket rings compress between the two faces. The joint gets sealed, pressure tested, scanned, and formally verified before anyone even considers moving to the next one. Module by module, the transparent segments link into a single unbroken corridor beneath the sea. From the surface, the finished line would look like a faint blue glow tracing its way along the seabed. From inside, it would eventually feel like walking straight through the ocean itself. But a sealed glass tube isn't a transport system on its own, and this is where the vision has to get rigorous again instead of purely beautiful. Emergency flood doors go in at both transition points, where the conventional concrete tunnels meet the transparent modules. Drainage channels and sump pumps get wired through. power conduits, communication cables, ventilation ducts, monitoring cameras, leak sensors, signal systems, and control networks all get threaded in and connected. The rail bed sits on vibration isolation pads, with steel rails laid, aligned, and checked, power rails connected, and every signal sensor calibrated and independently tested, all before a single passenger comes anywhere near it. Once the tunnel is finished, the vigilance doesn't stop. It just changes shape. A structure like this would realistically run on something close to a digital twin, a continuously updated computer model fed by thousands of embedded strain gauges, pressure sensors, and vibration monitors threaded through every module, comparing real-time readings against the structure's expected behavior every second of every day. Japan already runs exactly this kind of real-time sensing at national scale for earthquakes, with a public early warning network that can detect a quake at its source and broadcast a warning to phones and trains before the shaking even arrives. It's the same basic instinct behind Japan's bullet trains, wired to detect the first, faster-moving tremor of an earthquake and begin braking automatically before the slower, more destructive shaking ever arrives. A structure sitting on the seabed instead of solid ground would need that same reflex, just aimed at water pressure and structural strain instead of ground motion. Predictive modeling would likely play a growing role over time, too, with years of accumulated sensor data eventually letting engineers forecast wear on specific seals or panels months before a physical inspection would ever catch the same problem, shifting maintenance from a fixed calendar schedule towards something closer to preventative medicine for a 55-kilometer patient that never gets to rest. The tunnel safety architecture would also almost certainly borrow from submarines rather than ordinary rail tunnels. The entire corridor divided into independently sealable compartments, so that if any single section ever did detect a breach, watertight doors on either side of it could close automatically, isolating the damage to one segment while the rest of the structure and everyone inside it stayed completely dry and continued operating. The trains running through a structure like this couldn't just be repurposed commuter stock, either. Realistically, they'd need their own reinforced undercarriage and a fully sealed, positive pressure cabin system, so that even in the deeply unlikely event of a breach somewhere along the route, air would be pushed out through any gap rather than water being pulled in, buying passengers and crew critical extra minutes before any secondary safety system even had to activate. Propulsion would likely run on a redundant, distributed system rather than one central engine, spreading motors across multiple cars so that losing any single unit wouldn't strand a train mid-crossing in the one place on the entire route where a breakdown would be hardest to reach. Evacuation planning would follow logic borrowed from both rail and maritime safety standards at once, with the emergency walkway running the interior length of every module doubling as an escape corridor, sized and lit specifically so passengers could walk to the nearest concrete transition zone unassisted if the rail system itself ever had to shut down mid-journey. None of this is exotic technology in isolation. High-speed rail already uses distributed propulsion. Submarines already use positive pressure hulls, and cruise ships already build compartmentalized escape routes. This concept just asks, what happens when you combine all three disciplines into a single vehicle running through a single structure for the very first time? A realistic service pattern would likely run trains at fixed, widely spaced intervals rather than the near-continuous frequency of an ordinary metro line, partly for safety margin between vehicles inside a structure with fewer escape options than open track, and partly because a journey built around the view outside the window would lose its entire appeal if it felt like standing in a subway car during rush hour. The first thing to move through the finished tunnel isn't a passenger train at all. It's a small, unmanned inspection vehicle, creeping along the rails, passing over every module joint in sequence, while its sensors log vibration, structural alignment, power stability, and any hint of a leak. Only after that clears does an empty trial train run the full length of the tunnel, proving that the rail system, the flood doors, the sensors, the lighting, the drainage, and the ventilation genuinely function together under real conditions with nobody aboard to put at risk if something fails. Only then does the construction site finally give way to something built for people instead of machines. Temporary guardrails come down, permanent transparent safety barriers go up, observation platforms get completed inside specially widened sections of the tube. Soft blue lighting threads along the titanium ribs, and the glass itself gets polished until the ocean beyond it looks genuinely clear rather than merely visible. That's the moment the tunnel stops being purely an engineering structure and becomes something closer to architecture, a cinematic space built beneath an entire sea. Long after opening day, the maintenance regime never really stops, either. Fleets of small inspection robots, crawling slowly along tracks fitted to the tunnel's exterior, would realistically patrol the whole structure on a rolling schedule, checking glass clarity, seal integrity, and any early sign of biological growth on the outer surface. Because marine organisms colonize any submerged surface eventually, and a coating of algae is a cosmetic problem right up until it starts hiding a structural one underneath it. Running an inspection program at that scale wouldn't be cheap or occasional. It would look more like a dedicated, permanent workforce, a mix of human divers and autonomous vehicles working in rotation for as long as the tunnel stayed open, because a structure like this never really finishes being built. It just enters a permanent, decades-long phase of being watched. A project this ambitious would almost certainly never get built in one continuous push, either. The more realistic path would start with a short pilot stretch. Maybe a single kilometer of transparent module inserted into an otherwise conventional tunnel, somewhere with calmer water and shallower depth, built specifically to prove the concept at small scale, gather years of real operating data, and let engineers watch how the glass, the seals, and the titanium actually behave under real tides and real marine growth before anyone committed to 50 kilometers of it. Only after a pilot section like that had run successfully for years, weathering real typhoon seasons and real inspection cycles, would a longer, full-scale crossing become something a government could responsibly fund rather than simply propose. That's not a limitation unique to this idea. Nearly every genuinely new category of infrastructure in history has followed the same pattern. A small, almost timid first version, watched closely for years, long before anyone attempts the version ambitious enough to make headlines. Who would even pay for that first version is its own open question. A project at this scale would likely need to be structured the way Japan's largest infrastructure has often been funded before. A mix of national government backing, private rail operators willing to bet on tourism revenue alongside ordinary commuter traffic, and possibly international investment from countries watching closely to see whether the concept actually works. Because whoever proves this technology first would hold a genuine head start on every other coastal nation, quietly wondering if their own ferry routes could be replaced by something more permanent. When the first passengers step inside, they aren't simply boarding a train. They're stepping into a version of travel that doesn't exist anywhere on Earth yet. On one side runs a polished observation walkway, on the other, the rail line itself. All around them, curved glass opens directly onto the deep ocean, drifting fish, quiet currents, the slow blue light of a world most people only ever see through a screen. Outside the glass, a train glides past through the neighboring tube, its reflection sliding silently across titanium and curved glass at once. The whole experience sits somewhere between reassuringly safe and quietly impossible, precise in every engineered detail, and dreamlike in exactly the way it feels to actually stand inside it. The sensation changes the deeper the train goes, too. Near the shore, the light overhead still carries a hint of surface brightness, and shapes stay sharp. Further out, the color shifts toward a deeper, cooler blue, sound softens, and the cabin lighting adjusts automatically to keep the transition comfortable instead of disorienting. Somewhere near the midpoint of the crossing, At the deepest and darkest stretch of the route, the tunnel's own lighting would likely become the only real light source visible in any direction, turning the glass into less of a window and more of a slow-moving aquarium wrapped entirely around the train. A few widened observation cars might even let passengers step away from their seats entirely, standing directly against the curved glass with nothing but a safety rail and a few centimeters of titanium and laminated glass between them and several atmospheres of open ocean. Near the far end, as the tunnel begins its gentle climb back toward the northern shore, the light would shift again, brightening gradually rather than snapping on all at once, giving passengers a slow, deliberate return to the surface instead of an abrupt one. One or two of the widened modules along the route might function less like transit infrastructure and more like a destination in their own right. A small lounge car with seating angled toward the glass, where passengers could choose to simply wait for the next scheduled train rather than ride straight through, treating the crossing itself as the point of the trip rather than an obstacle between two shores. None of this exists yet, and that's worth saying plainly one final time, because it matters more than the spectacle does. This is not a real Japanese infrastructure project under construction anywhere today. It's an engineering fantasy, built deliberately out of real materials, real methods, and one very real precedent, a country that already proved, back in 1988, that it could bore more than 50 kilometers beneath an unforgiving stretch of ocean and come out the other side with something that simply keeps working. It's worth remembering that Seikan itself sounded exactly this speculative once. In the years right after the Toya Maru disaster, boring more than 50 kilometers beneath one of the roughest straits in the Pacific, through rock nobody had properly mapped, using technology that hadn't been proven at that depth or that distance, sounded to plenty of contemporary engineers like exactly the kind of fantasy this video keeps insisting it is. It took roughly 24 years, 34 lives, and a level of stubbornness most infrastructure ministries don't have. But it got built anyway, and it's still running trains today, decades later, without most passengers giving it a second thought. Japan wouldn't even be the only country flirting with ideas this bold either. Norway is separately developing plans for submerged floating tunnels as part of a coastal highway project meant to eventually replace a string of ferry crossings along its fjord-cut western coast tunnels that would float, anchored below the surface, rather than resting on the seabed at all. China has spent decades studying a comparable ambition of its own, a proposed tunnel across the Bohai Strait connecting Shandong and Liaoning provinces that, after years of feasibility studies, still hasn't broken ground, precisely because ambition and feasibility are two different currencies, and mega projects like this one live or die on whichever currency runs out first. Different countries, different mechanisms, same underlying instinct. When a strait becomes inconvenient enough for long enough, someone eventually decides it's worth inventing an entirely new category of structure rather than accepting the delay forever. None of that makes this specific concept real. Realistically, an idea like this would still need years of feasibility studies, an environmental review process at least as demanding as anything Seikan or the Aqualine went through, and a construction budget large enough to make even Japan's infrastructure ministry pause before signing off. Nothing in this video is a promise. It's closer to a bet, laid out piece by piece, on the idea that the distance between clearly impossible and quietly operating has mostly ever been a matter of time, money, and enough people willing to keep solving the next problem instead of walking away from the first one that looked unsolvable. Every tunnel before this one was engineered to make passengers forget the ocean was ever there. This one is engineered to make them remember it, on purpose, the whole way across. What that vision really reflects is an old human impulse wearing brand new materials. The pull to cross boundaries that water used to make permanent, and to turn the act of getting from one shore to another into something worth experiencing in its own right, instead of something you simply endure with your eyes closed. From the first seabed survey to the last polished pane of glass, this is a story about ambition, precision, and the quiet possibility that what looks impossible today is really just tomorrow's blueprint, waiting for someone patient enough to